Tell me when. Tell me when you can see the screen.
Yes, we can see it.
Excellent. Okay. Okay, I want to test the function so that I can see people's chats. Moving the slides without being in a different window. Apparently it's not working. Let's see, does this work? Okay, I'm going to use two windows then. Okay, so hi everyone, welcome back. This is week 3. You're not going to believe this. I thought I was only teaching 2 weeks, and then Ibrahim was like, by popular demand, we need you back. I was like, I got you. That's a joke. But I guess, I don't know. Let's jump right in. So if you remember the past 2 weeks, and this is week 3, or this is the 3rd session, we've been talking about the principles of, we started with the principles of doing the scientific method and sampling and probability sampling, and, you know, how you pull your sample into, how you pull a sample into a data set. And then we also talked about, now that you've got your sample into your data set, we talked about probability sampling. And what I want you to take away from that is sometimes your probabilities are not the same for all. You cannot have an equally random sample. Some are more weighted than others. Many times, most of your studies are a convenience samples, you know. And so there's no fine line. There is no hard line for how to do some of these things, but there is thoroughness, you know, to borrow a Nigerian expression. You cannot just do things anyhow. There is rigor, there is thoroughness, but it is not dogmatic. And then we moved into the principles of the linear regression. And what we said was that a linear regression just obeys the properties of numbers, particularly continuous numbers. We said a continuous number is one in which between 2 points, there's an infinite number of numbers. But someone asked a very interesting question, very good question. They said, what do we do with discrete variables? And I said, most times we treat them as continuous numbers, like the numbers of teeth in your mouth. If you wanted to predict the numbers of teeth a baby would have at every weight for age, the numbers of teeth in the person's mouth maybe can go up to, I don't know, what's the highest? 32 is what we call normal, but maybe people can have supernumeraries, or maybe they can have less. But I doubt that the number of teeth in people's mouth on average would go beyond 36 or 40, let's say 40. And so you see, between 1 and 40, first of all, you cannot have 1.0001 teeth. You cannot have 1.1 teeth. You either have 1 tooth or 2 teeth. So that's discrete. But if you're predicting the numbers of teeth in a person's mouth, you probably are going to use linear regression. And you're also going to run into that challenge where you're going to say, if the weight of the baby is 0, you expect to have XYZ number of teeth on average. And you say there's no way in the world a baby who's alive, even a baby who has passed, can have a weight of 0. So you can see that there are limitations of linear regressions. There are limitations of the scientific method. They are not cast in stone. However, this does not mean that you should join the people who are anti-science or the people who are anti-intellectual. there is a rise of anti-science and there is a rise of anti-intellectualism in the world today. I think it's because our educational system is really, really horrible all the world over, not just wherever you are. And when people cannot get the level expected of them, it's a story of sour grapes. If you don't know the story of sour grapes, a fox was trying to get some grapes. The more he jumped, the less he could get at the grape. And then he walks away saying, those grapes were bad, those grapes were sour, that's why I could not get them. The reason I've told you all of this is if you know the limitations of the work that you're doing, and then you can move with some humility in the world, and you can move with some thoroughness. You can do the best you can, knowing the limitations. Let's bring that all together. Now, we started talking about what does it look like when we've done a good job in terms of the linear regression. And where we ended is this page that we are on, the R squared. And the R squared is the coefficient of determination. It is a measure of goodness of fit. How good, how strong do we think our model is? Remember that a linear regression predicts. We say that if we know a quantity of X and we vary that quantity by 1 or by 2 or by whatever X amount, if we vary X by X amount, how does Y shift? We're predicting Y. And we use a line of fit to say this is on average we expect. And we did that exercise where we saw that somebody might not have the expected, and that is because of variability. And so we talked about variability, but we also, the point here, remember, this is about the principles of linear regressions. You need to understand what is working behind this. What are the assumptions that we have by convention, not by an establishment of truth, but by convention? What have we agreed? And we have said, on average, we expect. So some people are above the average, some people are below the average. And you can begin to see how science is really based on philosophy. On average, the principle of exchangeability. The average person on the street is not the poor person on the street. It is one person selected at random. It could be the head of state. It could be the homeless person on the street. But what we have assumed is that because people are people, you can swap one for the other. So coming back to goodness of fit, coming back to your coefficient of determination, what I left you with last time was that if you go and look at your linear regressions for anything from smoking versus lung cancer to malaria versus productivity later in life, look at the R squared. We say the R squared is the measure of variability in Y that is determined. The measure of variability in Y, yes, that is determined by the variability in X, and it is measured as a percentage. Where this R squared here, forget about this for a second because this is a simple linear regression, where this R squared here is a 1%. So we're saying that, yes, it may be true that X predicts Y, but to what extent? We're saying when X varies by 1, when the prediction of Y by X, in terms of when X varies, how does Y vary, is only contributed, the contribution is just 1%. 1%. So again, think about this. We say we found a statistical association, but this variability, the prediction, the contribution to variability is a 1%. You know, how much is that meaningfully useful to you when you're thinking about your work, when you're thinking about establishing the truth about the relationship between these two things? And what predicts the remaining 90%? Unknown confounders, errors, errors in measurement, systematic error. Not everything in nature can be the same, because what is the point of that? And so today, we're going to move into, make it a little complex. We're going to talk about more assumptions about a linear regression. So I'm telling you the good things about linear regressions, how they work, but I'm also telling you the limitations so that you go forward with a knowledge of what you can confidently assume and what you can say, hold on, let's think about this. Let's have this discussion on where we're going with this. Okay, so we've done this one already. Have we done this one? I think so. I think I was telling you about, look at this here. look at this negative adjusted R square, you know, and you say, oh, how can a squared be negative? And I was telling you that it's just sometimes garbage in, quote unquote, garbage in, garbage out. A regression is not your SPSS, your Stata, your Python is not a machine of truth. It is just a machine, and it spits out the properties of numbers. It is agnostic to the variable you're measuring. Keep that in mind and become a subject matter expert in the thing that you're working on, so that you don't run away with results of that are spat out by your SPSS or your Python or your R. Rather, you're focusing on what is the principle. What do we know to be true, not philosophically true, but what do we know to be factual in science, and how do we move forward? The last thing I would say before we move forward is this. When you do research, I want to challenge you to do research that is useful. Don't just crunch numbers. When you look in your environment, you say, oh, what can we do to change this? And who needs data? And how would they use this data to change things? Rather than say, oh, I'm interested in X, Y, Z. Oh, what are we going to use it for? Well, I'm just going to publish a paper. Well, that's great. Thank you for publishing yet another paper that we can see on PubMed and Google Scholar. Okay, jumping right into, so we have simple linear regression, important variations. Yes, let's do this one. So this is a simple linear regression, but in this case, remember we said you have a continuous variable, but in this case, your predictor, your X variable, is dichotomous. What does dichotomous mean? It means yes or no, it means 1 or 0, it means happy or sad, it means standing or sitting. Basically, you can answer the question of the X variable in 2 answers, either yes or no, 1 or 0, etc. Okay, so let's look at this example. You overhear 2 colleagues arguing about whether the number of hours worked by male and female residents at your hospital were different on average. So you see, this is a dichotomous variable. This is a dichotomous variable because you are either sex at birth assigned male, or sex at birth assigned female, or you're either male or female in terms of sex. And so you say, okay, so last class we used, no, we did not do that. That was not us. But last class we used the t-test to examine this question. Another way to do this is using the linear regression. So that was somebody else, not me. But we did use, but let's look at this question with a linear regression. So we're saying, so look at this. If you remember your y is equal to beta naught plus beta 1 plus x, this is what you have. So, excuse me, I'm going to call somebody. Did you guys think I would not call someone today? I definitely will. I see a name, Ten Chong. I like that name. If you are interested in participating, unmute yourself. You would be the star of the class. I also see Marufat. I see Jerry. Jerry, 3 weeks in a row. Good for you. Thank you so much. Let's see. I was about to make a TikTok joke, even though I don't have TikTok. I was about to say thank you for the lion, guys. I see Sabina at Hiambo. If you are interested, or anyone who wants to volunteer, please unmute yourselves. I'm going to ask the questions now. Why do we have B beta 1 female instead of beta 1 gender? Does anyone know?
We want to test for the hours worked female first.
Okay. Okay, someone else came up. So you're saying we want to check for the hours worked by females first, okay? Someone else?
I think female is the reference.
Female is the reference, okay? 2 different answers, I like them. A third answer? Stay unmuted. Stay unmuted. If you're at the start at the moment, stay unmuted unless there's noise in your background. So someone said we want to check for the female. and I like it, but it's not exactly correct. And the author said the female is the reference. And that's a good point, but it's not exactly correct. But I like it, it's very strong. Let's move from there. Male is the reference. So that is why you're looking at the beta for female. So this beta, remember that this beta, okay. So because we're talking about continuous variable, last week we also talked about sometimes your output is a ratio versus a mean, an interval number, a continuous variable, a mean difference. So let's say very strongly here that whatever variable you see after beta naught, the other thing is the reference. So in this case, male is the reference. And what this beta naught signifies is the value of female above or below the male. So if it was plus beta 1, if our beta 1 was negative, right, that means that females have reduced. If beta 1 was positive, that means females have increased compared to males. So that's a good point. So we can't check what it is for female. And you would need another set of codes to do that. I forget what the codes are in Stata, but we're not using Stata, so it wouldn't even apply. But we could check that. But when you see whatever you see here after beta 1, the reverse, the complement rather, is the reference. Okay, so that means that B naught is the average for men. And so you would say that females have B naught, that is male, plus whatever B1 is for females. And remember, B1 can be negative. Okay, so good discussion. So let's look at this. And this makes my point. So let's start from here. So we see variables entered female. What is here? Look at our adjusted, look at our R square, 1, 2. So this is a 3.2% prediction. But what is our p-value? Look at our p-value, it's significant. So you go, you run, you publish, you say, my God, females work less than males. And you are right. But look at this adjusted square. Just keep this in focus. You're not going to say, oh, but the goodness of Pete. It is just a thing for you to think through as a scientist. So what basically it means is that there are other things. There are other things you need to consider. And we're going to do that when we go into multiple linear regressions. There are other things to consider besides just sex. So we're using sex here, not gender, because sex is your assigned biology and gender is your expression of yourself in terms of that assigned biology. So we're talking about sex here. Okay, so we're looking at this. We see the significance. It's significant. We see the okay. This is the value -6. And so we're saying that the beta coefficient is -6.5. This is hours worked per week. We infer that females work 6 or 7. Let's call it 7 hours fewer. So remember that this is negative, and if we go back, we have a plus sign. If you remember your GSS1 or junior secondary, plus minus, plus multiplied by negative gives you a negative. So oops. So we're saying that they work 6, 7 hours less than. This is significant. So you reject the null that there is no difference in hours work, and you conclude. I said this is supposed to be sex. Let's call it gender. Let's just go with that. Conclude that gender was associated with the number of hours worked by resident doctors at Lagos Hospital. Okay, so you can see that male is the reference compared to males. Female worked 6 hours less. Okay, so no.
Sorry, sir.
Yes, go ahead.
Excuse me, sir.
Yeah.
I have a question.
Yeah.
I'm just a little confused as to looking at the question. It says the hours work. If you can go there, if you can go back one slide, let me see. It says hours worked by male and female. resident doctors.
Yeah.
So how did we come to the conclusion that the male will be the reference? Is it because it's appearing first in the question?
No,
or
that's a really good question. Who's asking that?
That's me. That's me, it's Jerry.
Good. That's a really good question. So I skipped it, and the answer is found in this line here. So I'm going to say it for the fourth time. It's a really good question. It depends on how you code it in your data, and so some people would code male as 1 and then female as 0. And when whatever you code as the higher number, the lesser number becomes the referent. So this is the reason why the male is the referent. So you can write this as and say this is what you are trying to do. But if you code it differently, for example, if you coded males as 1 and females as 0, your male will automatically become your female will become the referent, whatever the lower number. So some people will code as 1 and 2, so 1 will become the referent. Does that make sense?
Yes, makes sense. So we are going to put instead of predicting, we just maybe like in the previous one we did, instead of referencing training now, instead of referencing I think the last one was hours of residency training or something in relation to hours worked. So when we have a dichotomous variable, both of those variables enter into the regression equation. Yeah.
Exactly. So I get what you're saying, but you see, because we are still talking about simple linear regression, a simple linear regression is just one x variable. If we had a, let me see, I think I can squiggle. Let me try this pen. Okay, if we were talking about multiple, what am I doing? Okay, let's not squiggle. If we're talking about multiple, linear regression, then there would also be another variable of residence years. But in this example, we are done with that question of residence years versus hours worked. This is a new example of hours worked between men and women. So question 1, hours worked depending on your year of residency. Question 2, hours worked whether you are a male resident or female resident. So you answer those questions individually. But a better way is to combine all your x variables, and that's what happens in a multiple linear regression. You see, and that is why, remember I was saying that you see this 0.32 as your R squared. I said there are more to explain. So when we combine them in a multiple linear regression, let's look out for whether this R squared improves or reduces. Okay? Are you clear on that?
Yes, sir. Yes, sir. So one final question. Yes. In this case, you said the beta naught is what? Average hours worked by?
By the man. By the
reference.
By the reference, exactly. So therefore, let's go to look at this. So this constant, remember your constant is your beta naught. So you're going to say, so basically you're going to say on average, men work 74 hours per week and women work 74 hours plus minus 6, which turns to 74 minus 6. So you're going to say on average, women work, what is 74 minus 6? 68 hours a week compared to the men who work longer.
Okay.
Do you see
beta
that?
One becomes, yes, beta 1 becomes
your constant, your multiplier, or your mean difference in a dichotomous variable. So beta 1 is compared to the reference. So without even caring about what beta 0 is, once you know beta 1, you can see compared, remember, compared to the reference, compared to males, females work 6 or 7 hours less. But remember that a linear regression is a prediction. And so this number of hours worked. So if they say, how many hours do residents work? How many hours do residents work in a teaching hospital? And you would say, well, on average, we expect that people would work this constant. But we're now saying, if we now consider them to be male or female, if they are female, remember that female is 1. So beta minus 6 times 1 is minus 6. So females will work your constant, your average, minus 6 or 7. And so you say females work whatever that answer is. And males work, because coded males are 0, beta times 0 is 0. So you say males work beta naught. Okay, let's move forward. We have 35. I can answer questions at the end, but you can see that we've just talked about, or we've just gone through what we're talking about. This is the prediction mechanism. You're trying to predict how many hours residents work, you know, and you're saying on average, if we average everybody out, we are going to see about 74, I believe. But if they're males, if we look at the males versus females, no, not if we average everybody out, because beta naught is for males. What we're going to see is that if you are male, because this is the reference, you're going to work 74 hours. If you're female, you're going to work 74 hours plus minus 7 hours. And so you have predicted the number of hours people work using your formula or your regression. Okay, so no, let's skip this because we did not do t-test the last time. So we continue here, and we're saying the predictor variable. Remember that in a linear regression, in a simple linear regression, we're still talking about simple linear regressions. So we have only one x. You know, we are saying we say that in a linear regression, your y variable, your dependent variable, your outcome variable, your response variable, all the same thing, depending on what field you are, depending on what you remember to call it, that is continuous, right? But we said that your predictor variable, your x variable, your whatever the independent variable does not have to be continuous. It can be continuous, it can be dichotomous, it can be categorical, different categories, you know. So let's see. So now we're doing another question. We're saying, is the number of children a resident has related to the number of hours they work? So maybe this question is a policyholder is trying to understand, like, our residents burning out, and do residents who burn out, do they really learn anything? Are you just keeping them in the hospital and you must work, but they really are not learning anything? And the policyholder says, what about, does it differ amongst men and women? And does it differ if a resident has children or has a family? You know, what is the optimal the number of hours that our residents should work to have optimal training? So you can see that this is useful. Like I said earlier, you want to do research that is useful for decision making. Okay, so now we're asking a third question. It's a different question, but it's related to the other two questions. Is the number of children a resident has related to the number of hours? There are a number of ways to analyze this children variable. First, as if they are continuous. So, so remember what we said. These are discrete. You can't have 1.1 child. Well, if we have 1.1 child, I would like to have a 0.1 child as opposed to a whole child because maybe they are less trouble. But unfortunately, I cannot have a 0.1 child. I either have the entire child or I don't have the entire child. But we will treat the number of children as continuous. Remember, I also said, I know that people can have as many children as they want, but I don't know that anybody in the history of the world has had over 250. So you see that there is a bound, but we're going to treat this as a continuous variable at the same time. There is a bound. So it is not a property of a continuous variable not to have a maximum bound. The reason I'm telling you, I talk about the maximum bound is because of the prediction. If we know in reality the number of teeth in your mouth cannot go past 42, then if your output is telling you that the expected value when x is so and so is 64, you're like, in reality it does not go past 42. So how can we have a prediction of 64? Again, it's the property of numbers that it is telling you, not it is agnostic. SPSS does not know that you're talking about teeth. Maybe AI knows you're talking about teeth, and maybe you can ask it what to do in these situations, but just letting you know the limitations. Okay, so now we're going to go through a range of ways that you can address this question of if a resident has children, does it impact the way that they work? All right, so treat as a continuous variable. Let's look at the output. So we're saying, okay, so somebody else, unmute yourself and tell me. So read this slide, or don't read the slide, just look at this here. Tell me what beta naught is, what beta 1 is, and what x is. Just tell me about this question from this formula. Anybody? Any takers? I see Fatima Idris. Ali, I see Humphrey. Humphrey was a star last class. I see a really nice name, Jessica Single, and Matthew Kandabira. I hope I pronounced that correctly. Anybody? Okay, I will tell you. No takers, I will tell you. So we know that we are trying to answer the question for how many hours we worked or are worked, per week. And but the question is, if a resident has children, or is the number of children a resident has, does it predict the number of hours? So the number of children. So let's start with beta naught. So we're going to say that, let's imagine that people can either have 0 or greater than 0 children, right? So people can have 1 child, 2 children, so on. And so we would say that our our reference is 0 children, right? So you have 0 children, and then someone has 1 child, 2 children, and so on. And so beta naught would be what happens when the residents do not have children. So for every increase in the number of children is your beta 1. Okay, so let me tell you something. If you are a little bit anxious about interpreting this, this thing is not in my brain. It's not something I remember. So even when I'm presenting this slide, and I contributed to making these slides, I have to think through it. I have to analyze it from first principles. And that's why sometimes I say, hey, I thought this last time, but I don't agree with it today. If you remember our first class, we had those discussions. So feel free to walk through your thinking. And I think that makes you a better scientist. You always have to challenge the null in your head, not just with SPSS. Okay, so basically, we're saying that your beta naught is if you have 0 children, right? Because you can see this table here, there is 43% have 0 kids, and then others have 1, 2, 3, 4, 5, 6 kids. Now look at the upper bounds. Only 1 person has 6 kids. So how many people have 7 kids? That's a simple answer. Does anybody know? Shout it out. How many people have 7 kids?
Zero.
Nobody.
There you go, 0. So the upper bound is 6, but we're going to treat this as a continuous variable. Okay, so nobody has 7 kids, the upper bound. How many people have -1 kids? Nobody, you can't have -1 kid. Okay, so look at our constant. If you have no kids, our reference is the people with no kids. Why is our reference the people with no kids in this case? This is different from male, female. We did not code male as 1, female as 0 in this case. This is a continuous variable. We did not have to code. We just put in the numbers. How many kids do they have? So don't mistake this here for the codification of the number of kids. This is a continuous variable. It is just the number of kids they have. So when I say the reference is 0, it is not exactly a reference per se. It is that you want to be able to say, it's not a reference, but you need to explain what your constant is. And your constant is when, remember your constant is what your y is when your x is 0. So let's go back to this. We're going to find this hard to. Okay, let's look at this one. This one here. So forget about the actual question. Remember that your beta naught is your constant. And if we go back there you go, found it. If we go back further, remember that your regression line is really this. And you can see that C is your constant. C is your beta naught. And you can see this is C. This C is Y when X is 0. So I'm going to be quiet for 1 second, if I can manage that, so that it sinks in. But I'm going to say it again before I'm quiet. Your beta naught, which is your C, is the value of Y when your X is 0. You can see that here. X is 0, but Y is a non-zero figure. Your beta naught, which is C, is your Y variable when your X, not your X, but when your X variable is 0. Okay, something told me it's sunk in. So let's go back.
I have a question, please.
Go ahead, please.
I wanted to understand why we are using number of kids as continuous variables.
What would we use it as otherwise? It's a good question. So this is not a challenge. This is part of the course. What else would we use it as?
So I'm just thinking of what continuous variables mean, and that's why I'm asking the question, because as you said, there's nothing like 1.5 child.
Yes.
So that's why I asked the question. So I don't have an answer for what you just asked, but I just asked because of what continuous variable means.
Good. So it's a really good question, right? So and that's why I started, and I've always started these classes by telling you that we adopt this methodology not because it is true, but because it is the best we can do. And sometimes this is the best we can do to predict in terms of numbers, right? And you can get a sense of the relationship. So basically, let's look at the results, right? So look at our significance. Where's our significance? This guy. Unfortunately, it's not significant. Imagine it was significant. Imagine it was 0.008. Your question is a good question, and I'm answering it. I'm not pushing back. What we'll be able to agree on is that there is a relationship, right? There is a relationship between having a number of kids or having kids and the number of hours we work. So remember what I said, that research is for decision making. Now, if you know that there is a relationship, Maybe you can say, because there's a relationship, maybe we would have allowance for people who have families, you know, you can talk to your boss about it and get these allowances, these accommodations, right? Because we know there's a relationship. Someone might say, tell me the exact relationship, the quantity of someone who has one child versus two children. And that's where this may become significant. And then you would say, where is our coefficient? Yes, this is our coefficient. This is our beta 1. You would say for every child a resident has, the number of hours reduces by a quarter of an hour. And so someone will say, well, if you have 5 kids or 4 kids, it's only going to reduce by 1 hour. And again, it's not significant. So as a decision maker, imagine it was significant. You say, well, it only reduces by 1 hour per week. 1 hour per week, that's from 72 to 71. I don't really care. Majority of these people have what? They have between 0 and 3. So let's say the majority of them have 2 kids. So you're going to say that it reduces by half an hour every week, just because they have kids. So you're going to say, as the decision maker, they're going to say, I don't care about that. It's not significant. In fact, we're going to assume that they all work the same number of hours, especially because this is insignificant. So can you see why we're using this as a continuous variable? You can, number one, continuous variables, statistically, I believe they have higher, no, they don't. But many times you want granular, your most granular information from continuous variable to establish a relationship. And then many times, not all the time, you want to be able to quantify what is that level of prediction. And that is why you use this. But to your broader question, is it appropriate? And the answer is, maybe there is no better way to do it, because we know that these are not exactly continuous variables and there is an upper bound. So again, we come back to this. This is not established truth. This is the best way. So if for those of you who have taken the JAMB exam in Nigeria, what you may have realized that JAMB is not asking you for the correct answer. They are asking you for the best answer from your objectives. And that is why you should apply elimination. Why is this not true? Why is this not true? Why is this not the best? This is the best answer. And if you take JAMB again and you apply what I just told you, maybe you'll score 350 out of 400. But if you're at this point, don't take JAMB again so that they don't embarrass you too much. I hope I've answered your question. Well, let's move forward. Okay, so the beta coefficient is minus. We infer that for every additional child, it reduces by 0.3. It's greater than 0.05. We fail. We say there is no difference. So therefore, you cannot say, oh, these women with, men and women with children. You can no longer say, oh, residents with kids are disturbing. They don't contribute their fair share. You have your data. You say the number of kids does not. But let me continue to answer the question that was just asked, and we're going to see it. So what is another way to answer this question? Another way to answer this question, and another way to answer this question is to say, what about women with kids versus women without kids? And what do you do when you've done that? What have you done? You have dichotomized. So it becomes similar to this question. You have dichotomized. Instead of male, female, you have said no kids. You're going to code no kids as 0 and any number of kids as 1. And maybe that's better because that captures your bound, because you're saying any number of kids. What else can you do? You can categorize in an order category. An order category means there are hierarchies, because somebody would say, maybe somebody with one child has no problem working those hours as someone with no child. But what of somebody with 2 or more children? So you can have 3 categories: 0 kids, 1 kid, 2 or more kids; 0 kids, 1 or 2 kids, 3 or more kids. 0 kids, 2 to 4 kids, 5 or more kids. So can you see that now you can have a whole range of categories, and somebody is going to say, which one should we take? And the answer is, you take the categories either established in the literature or that makes sense to you as an expert. And we do that with age categories. Some people say, we're going to look at age categories from 0 to 5, 6 to 10. And you say, you're going to have so many categories because people live beyond 80 these days. You're going to have at least 16 categories. Why don't you group them? Somebody will say, why don't you group them according to child, adolescent, young adult, elderly? Some people will say, why don't you group them according to child, working age group, which is 15 or 18 to 60, or 65, and then the elderly. Somebody will say, why don't you just group it from 0 to 40 and 40 above? Why don't you group it to 60 above? And depends on what you are talking about. If you're talking about productivity, then maybe you look at, let's just move forward, because I think I'm over explaining this thing. Okay. Does anyone have a question, or should we continue to go through this thing? Question? I'm going to pause.
So sorry, just to confirm what I had in my brain. In the question we just solved, this particular question, our beta naught becomes the number of hours worked by average number of hours worked by residents with no kids. Correct?
Exactly. Because remember that your beta naught is your y when x is 0. So x is the number of children that a person has. When that number is 0, that is your beta naught. And it is equivalent to if you had a referent as 0. If you coded 0 in the number of kids and maybe and every other number of kids as 1, 2, 3, 4, this would be its equivalent, but they are not the same thing. But it's equivalent. This, in this case, sorry if I'm confusing you more. I'm just giving you extra information. This, in this case, is continuous, so there is no reference. But you are correct. Your beta naught is your y when your x is 0. Do you want to ask another question? Okay, if there's no other question, can you mute yourself? I can hear the noise in the background. Okay, so, oh yeah, who's that? I need you to mute yourself. Okay, good, thank you. Okay, now, remember what we said. So we started with dichotomous. A dichotomous variable is also a categorical variable, by the way. There are 2 categories, yes or no, 1 or 0, 1 or 2, standing or sitting, whatever. But just to make it clear, sometimes we separate them. It's a type of categorical variable. Okay, so now we can, and I talked about that to answer the question. I forget who asked the question. It was a female sounding voice. Apologies if you're a male. But so we said we can transform the count. So let's not go over this. Well, let's just do it quickly. So remember, this again is not this is a frequency table. This is not a coded table. This is not, we're not coding the number of kids. This is just your frequency table. It's a continuous variable. But now you convert it to categories and say, if they have 0 kids, look at 0 kids, 0, 70, 70. If they have, wait, what did we do here? Okay, good. If they have 1 kid, so this person said if they did the coding here, if they have 1 kid, that's another category, 1, 1. If they have 2 kids, 2 is 2. Remember, this is not a categorical table. This is a frequency table. This is a categorized table. If they have 3 or more, they are grouped. So 3 or more, look at 9 plus 4, which is 13, plus 1 plus 1, which is 15. If they have 3 or more, you group them. So these are categories. And this is why I was trying to explain just now I think it was Jerry's question about this, whether this is the nuance I was trying to make about this not being categorized. But look, by the time you look at this, you can see that it's almost similar. But this is your frequency table of continuous variables. This is your categorical table. 0 is 0, 1 is 1, 2 is 2, but 3 or more is grouped into one category. And this is what I was saying. And someone can say, why? Someone can say, why don't we have 2 or more? And if you have 2 or more, you have 0, 1, and 2. And 2 would now have a frequency of 28 plus 15, which, if my math serves me right, is 43. So do we see, to answer again this question that was asked, why do we use continuous? And my answer was, why not? Because you want to establish a relationship, because you want to quantify what that relationship is for every one increase, and because even though the number of children are discrete, we can assume with a high level of confidence, not with truth, but a high level of confidence, that it would make a continuous variable. And so we are satisfied to use it. I'm going to show you what we mean by high level of confidence in a visual representation as we go along. Okay, so here is a categorical variable, and this is where we run it. So now we run it. Jerry, you're the quickest to come off your mic, so please oblige me. Look at this categorized table. I mean, it's a categorical table. It's also a frequency table, but I just want you to know that this frequency table is for continuous variables, whereas this is for the categories, right? So unmute yourself, look at this table and tell me, because of time and because you're very quick, not picking on you, sir, but tell me, what is this? What does this tell us? What is our reference and what is our and just tell me about this formula here.
Okay, so our reference, B naught, B naught is going to
B naught is not our reference. Go on.
Sorry, our reference is those in the first category. Coded
What
0.
is the first category?
That is those categories coded 0.
Coded 0.
So that's those.
Right. Why is it
those that
0? Why not 3?
Because of course it's already coded 0, and we are looking at number of hours worked as the rankings in those categories increase.
Okay, so what you're trying to say is that the machine, SPSS or whatever you use, uses the least coded number as your reference, right?
Yeah, that's what it is.
Yes, it wouldn't use 3 because 3 is greater than 0. So that is why it's not automatically that the number of, if you have 0 children, that would be the reference. So if you coded people without kids as 3, and you coded people with 3 or more kids as 0, 0 will be the reference, and people with 3 or more kids will be the reference. Does that make sense?
Yeah, but then you would have to go. The results, the output may be a little confusing.
Exactly. So, there you go. That's a very solid point. So we are making things easy. So when you are coding your data, make things easy for yourself. That is why you should not have 16 categories of age. Have 3 or 4, sometimes have 2 categories. Make a balance between complexity and interpretability. Okay, that's a very good one. It will make things confusing. So you have said our beta naught or our reference in X is people with 0. Okay, now we have run this, but now we have run this as, in this case, it's very strange, right? We have run this as though, I don't remember, I don't know who that person was who asked the question, but I believe we've run this even as a continuous, as though these categories were continuous. And in Stata, because Stata does not know that you've categorized, if you wanted to run you wanted to tell Stata that your variable was categorical, you will put an I dot before your X. You will tell Stata, this is a categorical variable. In this case, we've not done that. So Stata believes that this table is the same as this table, but the upper bound is 3. And so it runs your results. So you can see why we said it's garbage in, garbage out. So we see the model equation asks when the independent variable, when X raises by 1 from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, how much does the response variable increase by when it increases by 1 unit? Okay, we're going to move into the assumptions of the linear, and that's where things are going to get crazy. Now, remember what I just said. From 0 to 1 is 1. From 2 to 3 is 1. That is called linearity. In some cases, things are not linear. The distance, the jump from 0 to 1, the distance between 0 to 1 is not the same distance from 3 to 4. Does anyone know an example of where things happen like that? The simple answer is with money. If you have $0 and you have $10,000, from 0 to 10,000, that jump may be very different from what an increase of $90,000 to $100,000 can do for you, right? That's a bad example, but it plants a seed in your head that not every variable is linear. 9 to 10 may be a very different relationship from 0 to 1. But we're going to talk about that. I've just planted that in your head. So if we assume, again, we're assuming that X is linear. So we can say when it moves by 1 unit, irrespective of 3 to 4 or 4 to 5 or 0 to 1, what does Y move by? Okay, so we've assumed linearity. And then we're saying, in this case, this means that as you go from 0 child to 1 child, or as you go from 1 to 2, this is you increase by, so this says this actually says you increase. And you can see that this value changes compared to the other one, which was the decrease, I believe, because of how, so you can see, so I'm not going to say how do you lie with statistics, but I'm going to say that you can see that how you've coded your data or how you've chosen to code or not code your data has basically changed the relationship. So once we transform this from this to this, you see, this was a negative when it was when we allowed it to be continuous. Once we transformed, our coefficient changed. It's now saying that there's an increase as you move from 0 to 1 or from 1 to 2 and 3 to 4. Okay? Now, but you can see that your significance is not significant. And if you remember your explanation, your definition of significance, what you are saying is that this value you're seeing is due to chance, is very likely due to chance alone. So you can disregard this value. And it does not matter that this is negative 2.5 or 2.25. The significance is also, you can say this is due to chance. So when it's due to chance, it's like if you float a feather in the air, where it lands, let's assume it's due to chance. It does not matter whether it lands in Africa or in the Middle East or in the Americas, it is due to chance alone. You cannot reach any conclusion. But we are assuming for the sake of teaching this class, if this was significant here, what we will be seeing is that your beta can change depending on how you categorize. So that is called fishing, when you start adjusting your variables to get a significant value. That's called fishing, and everyone holds themselves as scientists to a high level of honor. And you say, no, a priori, this is our categorization. We're not going to change it. We're not going to start fishing. We might allow for 1 or 2 changes, but we are not going to go on a fishing expedition. Okay, let's go. We are at the First hour, and we've not even got into the assumptions because this is a little tough, but let's go ahead. So another thing you can do, I don't like this one very much, and I usually skip it. But let's power through. So we've said you can keep them as continuous. We said you can dichotomize, and you can dichotomize as children and not children. You can, but you can categorize. Dichotomization is a type of categorization, but we use categorization sometimes when we're talking about the hierarchy, or sometimes when we're talking about more than two. There are other times that we categorize. They're nominal categories. There's no hierarchy. They're just different. Red sweater, blue sweater, green sweater. You know, those are different categories. So that's a nominal category versus 1, 2, 3, which is a hierarchical. Rich, middle class, poor is a hierarchical category. But here in this one, I've never seen this done in practice, but I don't know, they teach it in the stats classes, so I guess it's useful sometimes. Instead of using a continuous variable, what you do is you create multiple variables. So you're going to say variable one is X residents with 0 children. Variable 2 is residents with 1 child. Variable 3 is residents with 2 children, and so forth. And so if a resident has 0, all the residents who have 0 children are assigned 1, are coded as 1. And so in that variable, only the residents with 1 child are coded, with no children are coded as 1. And the residents with more than 1, with a child or more, are coded as 0. The reason why I smile about talking to you is for you to understand this, you have to have seen a data set table. This is another point. Get involved, as the more you don't be like, I'm going to make a joke. You know, sometimes doctors write prescription, and then if you ask a lot of doctors and you say, hey, can you pick out this pill that you've written from? If I give you 10 pills, you prescribe 2 of them. Can you pick out the 2 that you prescribed and the 2 that you did not prescribe? Sometimes it may be difficult. So sometimes you may not have looked at a data set, or you're not familiar with how data sets look. So this may be difficult. But basically, you know what? Let's keep this. Basically, you're creating multiple variables of 0 and 1 for the same variable. Let's keep this. We're out of time, and I really don't like it, but you have the slides. You can check it out yourself. If we have time, we're going to come back to do this. Okay, good. So that was the last one for the different ways you can explain your data. If we have time, we'll come back to this. Like I said, I really don't like it. I don't see the use. Just leave it as one variable. Keep it simple. Keep that one variable categorized. Keep it as continuous, and let's work. Now, and we're moving because we have less than 1 hour to go, and we still have some important things to talk about. So remember that we said, I started to plant the seed in your minds that for a linear regression to be factual, rigorous, there are some assumptions that have to hold. And I planted the seed in your mind that one of those assumptions is linearity. So we're going to talk about that. We're going to start getting into those assumptions. I also planted in your mind 2 classes ago about the goodness of fit. You know, what is the extent to which we think that, yes, X predicts Y, but what's the extent to which X tells the entire story about Y? And that's your adjusted R squared. So we're going to go into this, it's called diagnostics. It's like you do a test and you do a check. If you remember your mathematics, you say, prove that, blah, 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 or check your results. So you show the working, and then you do a check. I used to like that. I wasn't very good at math, but I used to like that. Proof thing. Okay, so now assumptions of linear regressions. Linearity. So we already talked about linearity. There's something called homoscedasticity, homogeneity of variance. It's very similar to linearity, and I like it. It's when you see the graphs, it's going to stay in your mind. Normality. So normality, people interpret normality as, oh, your graph, when you plot your data set on a what's that thing, on a normal curve, I forget what it's called, it should resemble a normal curve. But that's really not what it means, or I don't think that's what it means. It means that your residuals should be normal, should be normal when we're going to talk about that. Independence of your variables, a simple example is, if you are thinking about what is the height of men in Lagos, Lagos, Nigeria, and in your sample of 50 men, 7 of those men are from the same family. Those people are not independent. The data is not independent, because the 7 of the people being related, you are really predicting what's the height in that, average height in that family, not the height in Lagos. That's a good example. Your data has to be independent. We're going to talk about outliers. So remember this, where we had this beautiful frequency table. Oh God, I keep forgetting. Let's look at this beautiful table. So remember the question where we said, how many people have, it's very funny, the questions I ask, how they build into the later decks. I don't know if that is done intentionally, but it just seems to work. Remember when we asked how many people have 7 children, and the answer was 0? And that's because it's not on this table, and you can see that 100% of people are accounted for. But imagine in this table, imagine that in this table, somebody had 15 children, right? That is an outlier, or 25 children. They will be captured here, but it's an outlier because you can see from the cumulative percent that by the time you get to 4, let's even say by the time you get to 3 kids, more than 95% of the residents have been captured. So if someone has 15 kids, or if someone has 8 kids, that's really in the fringes, and that is outlier. That's and that's an outlier. Okay. So model specification. Okay, good. So when we talk about multiple linear regression, right, we're going to talk about multiple specification and multicollinearity. Okay, we have 15 minutes and we're going to power through, but I'm going to do my best if you have questions. I'm going to take a break here for 1 minute, and that 1 minute is to get my charger so my computer does not die. If you have any questions in the chat, please put it in the chat. I will try to respond to it when I have some time. So give me 1 second and catch your breaths while I go get my charger. All right, 1 minute is over, according to my wristwatch, I think. So let's jump right into linearity. Okay, so the relationship between the outcome and must be linear. Must, oh my God, must. Who said must? Okay, we said must. We want to assume, we want to believe that the relationship between the number of hours worked and the number of kids, or whether you have known the number of kids, is linear. Otherwise, you're forcing round pegs into square holes. No one knows what that means, but I guess maybe you do. So this, remember what we said in a linear, it's in the name, a linear regression. We're saying that when X moves, remember that whether you are at this point or whether you are at this point, one unit movement from X predicts movement in Y. But what if your graph really is like this? And can someone tell me what relationship can be like this? And I will tell you, it is quality of life versus quality of life, and let's see, so this is steeper. No, it's not quality of life. It's the reverse. Okay, now is not time to remember things because of time, but if anyone knows a relationship that is like this, after a certain point, it just blows, wow, and becomes much steeper. But even then, after a certain point, it starts to play too. Quality of life and income could be like this, if you earn well below the poverty rate, if that's your ex, and it keeps moving, but you're still below the poverty rate, your quality of life remains the same. But then, oh yes, it's a good example. But then you get above the level of the poverty income level, and your quality of life just starts to rise. And then you get to maybe a director at your job, a senior director, and and then your ex really doesn't move, your career kind of plateaus, your quality of life, it is just, nothing, it doesn't do a lot for you anymore. So maybe that's a good example. Maybe that's not a good example. But if that is the case, you cannot say that for every increase in X, Y increases, because maybe it's true around here, but it is certainly not true here. It is clearly not true here. Nothing is moving when X is moving. So if that relationship, and this is why I said you want to be a subject matter expert before you go crunching numbers. You need to know, you need to have read. This is what the literature thinks or says about quality of life in relation to the X. And someone will say, so why are you researching that if the literature says? It's because you're adding to the body of knowledge. You're answering a question in addition to what is already known. Don't repeat what has been done, except you are repeating it in a different population. But you have to have a sense of what this relationship looks like. Okay, now, how do you check for linearity? So think about other examples. But how do you check for linearity after you've done? And this is a crazy thing, right? Sometimes you have to have done the statistical thing first, then you go and check. And that is why the title is called post estimation. So you've estimated, and then you go and do your checks. So remember, I said it's like you prove something, then you show your checks. To check for linearity, something called a lowest scatter plot of the residuals. What is a residual? A lot of times we've refused to add in the residual, but the residual is denoted by that E thing. Ugh. Let's see if we have that. No, we must. Oh, there you go. Your residual, right? And so remember what we said again, like your X is not the sole predictor of your Y. Everything that is not predicted by your X is captured as a residual. So it's called error. I don't know if they are synonymous, but it's better to use the term residual because error might give you the sense that maybe it is not useful. And I'm going to show you where your error is or your residuals are. Okay, look at this. So this is your line of best fit, right? This is your line of best fit. And you're saying that if someone is at this point of X, maybe they have one child, this on average is where the number of hours they work. But look at this point here. I hope you can see this point here, this circular dot. But this, on average, we're saying this person is here, and this, where it meets the line of best fit, is the hours they work. But this is also a person who is here. So his Y is actually higher than our expected. So remember that the line of best fit is not the line of fit for everybody. It's the line on average, it's the line of best fit. And so this distance from this individual who actually has a higher Y, a higher observed Y than expected, that value is this fellow's residual. And this person, our expectation in terms of line of best fit is that E2, residual 2, or error 2, is that if you're at this point in X, we expect based on the line of best fit, that this is where your Y will be meeting the line. But you can see this individual is here on this point of X, but he's much lower than the line of the expected value of Y. So that Y observed minus Y expected is the residual for, it's right here. It's the residual for individual 2. Okay, we've been doing this since, I saw a note from Ibrahim from 2022. I'm like, Lord, we've been doing this for so long. So you can see that those are the residuals. So to do your post estimation, you plot a graph of, it's called a lower scatter plot of your residuals versus your X, not your X, but your X variable. And you expect the line to be, you expect your line of best fit, quote unquote, in this lower scatter plot to be a straight line. Is this a straight line? No. So you can see that, well, linearity is violated. Now, is this a straight line? I said no. Is this a straight line? Is this a straight line? Okay, let's look at some others. So, so is this a straight line? This red one, is this a straight line? Can someone tell me, is this a straight line? Anybody? Is the red line straight? Nobody? You can tell me if it's a straight line?
I don't think so.
You don't think so, right? So remember, we're not dealing with absolute truth. If I promise you, I promise you that if you run a regression and you see your line looking like this, better start celebrating. This is a straight line. This is as straight a line as you will get. So this, again, you see the point. This is another thing for linearity, but I'm just using that to show a line. Here, this is not a straight line. Why? The majority of the data is here and here. This is clearly a curve, right? So you cannot. So this is really just an eyeball test. But here, in this case, so remember we said it is your residuals versus the predictor variable. Let's see, is it your predictor or your predicted? It's your predicted variable. So it's your predicted variables. That's the variables. That's your variables on this line, the predicted, the expected. So you plot versus your.
Are we talking about predictor? Sorry to cut you. Do you mean predictor variable or predicted variable?
Predicted.
Are we talking about, for instance,
your observed?
Okay.
You're talking about predicted. Sorry. So it's the predicted is the values on this line of fit, on your best line of fit. So you're going to plot the distance, this E1 versus this, whatever this point here is. You're going to plot E2 versus whatever this point is. So E2 is this distance. I wish I could scribble. Oops. E2 is this distance between this point and the line, and your predicted is this value on the line for E2. Does that make sense?
So in essence, Y minus Y bar.
You're predicting, yes, Y minus Y I, right? Yes, Y hat minus Y I is your residual, and your Y hat. So basically, yes, exactly. Y hat minus Y I, but divided by or against your Y hat. That is your predicted value. And you can see here, this is from an actual research, and you can see that your line is, it's, you know, you take this, you show your professor, they're going to be like, oh, this is great. We're going to agree. We're going to agree that this is linear. Okay. So let's go to heteroscedasticity. So heteroscedasticity is, let's come back here. Can you see, and again, these things are, you're eyeballing them. Can you see that this, your data is fanning out from -4 all the way to +2 is fanning out, right? So, so for linearity, your line of feet would be your line of feet will cut through the data. No, that's it. Heteroscedasticity around 0, but your line of feet, it's going to be a straight line. So let's talk about heteroscedasticity. So look at this. Does anyone feel like this data actually fans out when you plot your residuals against your predicted outcome? Do you see a pattern here versus this one? Anybody?
It doesn't fan out. The first one does not fan out.
The first one does not fan out. So if you have the average of your residuals at 0, right? Your average of your residuals at 0, the distribution around 0 from your X, which is your fitted value, is different. If you look at this area, they are tighter around your 0, but they start to expand. They start to expand. So this violates your assumption of homoscedasticity. You say that this graph is heteroscedastic, and once it violates that, you would say that it does not fit the assumption of your linear regression. So therefore, what do you do? The question becomes, what do you do? The answer is that you don't perform the test, but you go ahead and publish your paper. No, I'm kidding. So you go back and you adjust your data. Oh, something I missed. Yes, so remember what we said, that regressions are just the properties of numbers, right? So what do you do when you find out, which is the point I was making? You don't go ahead and publish your paper. I was joking. But the question is, how many people do you think do a post estimation after their analyses? Tell me right in the chat what percentage of scientists you think do a post estimation diagnostic for their regressions when they run them. But the correct way to do this is when you run your post estimation diagnostic, when you see that the relationship may be there's a graph that a professor had. If your curve is this way, it's like a circle around the graph. If it's this way, if it's this way, it's this way, this way. There are different ways you can correct for it. So basically, again, I wasn't very good at math, so I'm guessing this is a quadratic graph. And if it's a quadratic graph, then your your formula should have the quadratic equation. So you can see that they add in the quadratic equation, which is your x squared. Do you need this? No. What you really care about is the relationship between x and y. And remember, so again, that person did not give me their name. It was a female. But they asked the question, so what do you do? Why do you use a continuous variable? And the answer was, because you're looking for the relationship. You really are just looking for the relationship. So you throw in this unnecessary, not unnecessary, quote unquote unnecessary, just to make sure that your data behaves like a linear. You correct for this quadratic thing by throwing in a quadratic function or whatever this is called, vector, into your equation to straighten out your curve, to straighten out this relationship. You take care of it because what you care about, and why I'm making this point is, think about this. You're looking for the relationship between anemia and income of the mother, or education levels, the years of education of the mother, right? And you find that relationship is curved. And then you say, let's make a variable called level of education of mother squared. Like if you went to school for 6 years, we'll square that to be 36. What does that variable mean in real life? It's nonsensical, but you throw it into your model because you want to correct for this curve, you know? And so that is, someone might say, no. This is Ojoro to the answer, or Ururu to the answer. And for those who don't understand Nigerian pidgin, it means that you are working towards the question from the answer. But that is not exactly true, because like I said, what you really care about is the relationship between your X and your Y. You're trying to predict Y from X. And so you're trying to take away the non-linearity, or you're trying to adjust for it or account for it by putting in this variable that may not make sense. That's why some papers you see a log transform. The log transform CD4 count. The square of the log square of the income. You're saying, what does that have to do with the price of bread? Why are we squaring these people's incomes? It's because we're trying to fit a model to establish a relationship. So remember, this is not absolute truth. We're using the properties of numbers. It is scientific divination, if you allow me to say that, to establish relationships. So we talked about heteroscedasticity. And okay, normality of the residual.
Sorry.
Yes.
Sorry, for heteroscedasticity. Sorry.
Yes.
It means
what do we
that,
do for heteroscedasticity? Yeah, go ahead.
Okay, so we would see a clustering of the residuals around.
So you're cutting in and out.
Okay,
so
I said,
what
can you hear me now?
Yeah, go.
So I'm saying,
no, you're cutting in and out.
Notice.
Okay, I'm just going to jump in because of time. If your data is homoscedastic, imagine there's a straight line from 0. The number of data points above 0 would be the number of data points, roughly speaking, whereas you cannot say that for this. Also, the distribution of the data, it won't fan out. Your data would be roughly equal in terms of the pattern. Those are the two things you look for when you're looking at heteroscedasticity. Okay, so let's move to, we talked about normality as another post-estimation test. So it's the normality of residuals. Basically, you expect that when you plot your residuals, they're going to give you a normal curve. And so to test this, you again plot your expected, your y hat versus your y, and again, you expect that it's going to be kind of along the diagonal straight. So is someone going to say this is straight or this is not straight? I say, you know what? This looks pretty straight. So this looks pretty straight to me. Relative to maybe this one. Maybe this one does not exactly look straight. But you can see this is normal QQ. So in fact, we agree that these two are straight. So you can see that these are really eyeball tests, and maybe it's a little naive to expect that it just falls entirely on the line, you see. And someone else might say, I care about doing a QQ plot because anyone can look at it and tell me it's straight when it does not look straight. Without this title saying normal, would you think that this was normal? Look at this deviation from the line here. Would you think that this was normal? But we're saying that this is normal. So these are things. The question is, what do you do? I think when you see these things, I think you go back and look at and try to, like I said, there's a chart that tells you what you should do when your relationship looks more curvy, but mostly it's a violation of linearity, meaning that your line really is not straight. It's really a curve. And then there's a quick fix, a chart. We don't have it here. I apologize. But basically, it's like if your curve is from left to right, bottom to top, this is how you should adjust for it in your model. If it's from right to left, top to bottom, this is how you should adjust for it. Maybe we'll look for that and we'll share with you. Okay, really quickly, I think we're doing good on time. Maybe not, but really quickly, outliers. So we already talked about outliers. We said, suppose you're looking at number of kids, and in this case, someone has 6 kids, right? Now, that means that that person is an outlier because the majority of people have between 0 and 3 kids. Okay, so a point is very far from the regression line. Let's see. So we talked about independence already. So good. Outliers. So we talked about what an outlier means, you know, from everyday discussion. But let's look at it when we plot our best line of fit. We say this is an outlier. You see this value when you have X here, your Y. Oops. No. When you have X here, your Y is supposed to be here. But when you have X here, observed, your Y is so far away. You're like, oh my God. So very quickly, why do we have outliers? Number one, outliers happen in nature. There are people with 16 kids, whereas most of the world, or most of the Western world tends to have maybe 2 to 3. And most of the, in Africa and other countries tend to have 3 to 4 kids on average, although things are changing there. But there are people who continue to have a larger number of kids. There's nothing wrong. I don't know if there's anything wrong with that, but that is natural. Number two is that there are mistakes from the data. So an analyst might be trying to enter BMI and then their favorite Korean drama comes in, and instead of 24.9, they write 249.9. You know, that could be a reason for an outlier. So go look at your data. That could be. And it might be important. Oh my God, maybe there's someone really with a BMI of 14 instead of 40. Do we need to seek medical intervention for that person? So go look at your data. Don't throw away outliers. What do you do with outliers? Some people remove them and rerun their model and see if anything changes. And we're going to talk about influence with that. Some people remove them, they run their data, they compare with them and without them. And they see, how does the outlier do? Does the outlier really influence our results? A predictor value is for leverage, a predictor value is very extreme. In examining BMI as a predictor of a BMI of 80 would indicate high leverage. So basically, for your outlier, I don't think you're looking at either your X or Y. But for your leverage, you're mostly looking at your X, right? You're looking at your X variable. And you're saying, this X is very, it's very large. And because you're predicting Y with X, that very large X variable would pull down or pull up your Y because of how extreme it is. And okay, so remember what we said, how do you address outliers or points of leverage? You take them out, you run your model, and you check whether your outlier or your point of leverage influences or changes your coefficient. So when you find out that someone has a sugar of 5,000, because maybe it was an error, I don't know if you can have a sugar of 5,000, but does it really change, And where does that apply? It applies in healthcare costs. Majority of people have low healthcare costs. Their healthcare costs are vaccinations, doctors' checkup, but there are some people who go so much, and those people are few. So do you remove them? No, not really. Leave them in the model and see, does it really change your coefficient? Most times it does not. And what do you do with an outlier like that? Don't remove them. Just because they use the healthcare system more than everybody else does not mean they should be removed from our analysis, because our analyses are used to influence policy and decision making. So therefore, just because your outlier can change your relationship or change your averages, it's a discussion to be had. Should we remove them? Should we say this is the real relationship? An outlier is still a member of society. They're still a member of the population. So their contribution to this relationship is this difference we are seeing. So should we leave them in? Should we remove them? Again, discussion, subject matter expert. Don't do research by yourself. Have people who you can talk to. Okay, so model specification. Okay, so let's jump model specification. Why should we jump it? Because we want to talk about multiple linear regressions as quickly as possible. No, we're not going to do this as quickly as possible, but we're going to try our best. Model specification has to do with a multiple linear regression, right? And that's why we jumped it. So we're going to come back to it. But let us see. So it was Jeffrey that asked the question, like, wait, we were talking about question one, number of hours worked versus resident years, or number of hours, resident years versus number of hours. And now we're talking about female and male. What is going on? And I said, because we're talking about two different questions, but in this case, we're going to now say, let us have multiple numbers of x's. Not your x's, but multiple numbers of x variables in one model, and let us explain what the contribution, the total contribution of all these x variables to the y outcome is. So we say number of reasons why we may have more than one predictor variable, and when you have more than one predictor variable, that is called your multiple linear regression. So remember, your multiple linear regression, your simple linear regression should be, what is the active word? It is linear. That relationship should be your y equals mx plus c. So to explain the variation in the outcome due to predictors operating together, because sometimes your predictors are not independently operating together. They are interacting with one another. They are adjusting with one another. Some of the components in, this is a bad example, but imagine that some of the components in being female are also in senior resident. Imagine that. I'm not saying that that's the case, and I'm not even talking about confounding. I'm just talking about statistical components. They are in there. So you want to have, like, what is that overlap adjusted for, both confounding, but also statistically. I've forgotten a lot of stuff, but there's something you do when you look at I've forgotten what it's called. Oh my God, I need to go back and read my textbooks. But there's something you look at, there's a code you run to say what is the individual contribution of each after you've taken out the overlap. And sometimes you want to know what is the value. And again, but your summary is called of course, you have to go to your coefficient of determination, and it gives you that total number from all of them combined, not individually. Okay, so and when you add an x variable to make it multiple, you say that you are adjusting for. So being a senior resident, or your status as resident, senior or junior, is adjusting for the relationship between being female or sex and numbers of hours worked. The sex is adjusting for the relationship of your resident status and numbers. So they are adjusting for each other. Basically, they're taking out that overlap and they're giving you their contributions. Okay, so let us look at a multiple regression that captures these adjustments. Okay, so our question is, so I don't want to ask this question because of time, but I'm going to go over it. We're going to see, now this is a dichotomous sex variable. If you're ever doing let's just go on. So this is dichotomous, and beta not female tells us that the analyst coded female as 1 and male as 0. And beta 2 tells us that beta 2 senior resident tells us that the analyst coded senior resident as 1 and junior resident or resident as 0. Okay, so let's look at the results. If you don't know how to understand an SPS output table, you're in good company. I don't either. I'm always deducing this from first principles. I look at it, I say, oh my God, what is this? And then I say, okay, take it easy, breathe. So I start to identify the things I'm familiar with first. That is how to understand this table. So now I'm doing the same thing while I'm talking to you. I see significance. I say, okay, I know what significance is. I see ANOVA. I know that this is the summary for the table before we even go to the variables. This is the summary of the regression table. If you've worked with Stata, SPSS, all that stuff, it gives you a model summary. Then it gives you the coefficients. So I'm like, okay, so our model, the entire model, this is an important point. The model itself is significant. When we go to the variables, we now look. You see this X variable, not almost insignificant. This other variable, not significant at all. But our model itself, our model is good. So we're going to jump up and down. We're on our way to publish. But let us look at that R square. Give us the R square. Where is our R square? R square is not here. So that's another thing. If someone sees it, tell me you see it, and then we'll talk about it. So our R square is not here. But you can see your output says your model is statistically significant. And how do we know that? It's your F statistic. Your F statistic is for your model, and your T statistics are for your variables. Okay, so let's not waste time here. We know our model is significant. We know that being female. So remember, can you remember the last time it was not significant? Being female was not significant, and the number of hours was 6.6 minus 6.6. So when you adjust for whether they are senior residents or junior residents, whether they are for their residency level, not whether they're junior or senior, that overlap takes out about an hour from female versus male, but it also removes the error. It also removes some error, and it makes your relationship significant. So now, going back to the decision maker, you're going to say, well, women in this hospital work less than men 5 hours every week. 5 hours is the time you can use to conduct 3 or 4 ultrasounds, 1 or 2 endoscopies, 2 or 3 cesarean sections. And so every time women clock out earlier than men, we are losing hours that can be contributed to procedures. Do you see how research is used to have discussions? Again, don't go into the stream of anti-intellectualism where people just talk about things without having sound logic or sound data to support. And your boss will say, how do you know? And you say, Jeremy et al. Conducted a study, and these are the results. Okay, let's move forward. So now, remember that we are talking about prediction, right? So therefore, you can say, oh, I don't like this one yet. We can say that, okay, let's not talk about the prediction. We skip that slide, but we're going to go into interaction. And maybe this is good because now we talk about interaction. I'm going to show us interaction with this picture. Not necessarily with this table, with this slide. Okay, so very quickly, someone is going to say what's the difference between interaction and confounding. So I'll show you the difference between interaction and confounding. Interaction and in interaction, you are looking, I was looking at this thing earlier today, and now I'm doing this first principle thing. So now I'm trying to remember what, in interaction, what you're doing, let's go back to what I said I would show you, is you are breaking the levels of a variable into its, you're disaggregating the levels of a variable, which is implicated in the relationship between your X and Y variable. And so let me show you here. What we care about is whether sex, right? The relationship between sex and numbers of hours worked. So if you if you look at the relationship between sex and number of hours worked, right? You would have just one, you would have male and female, right? But now you now introduce a third variable into this relationship. But that relationship, you are now asking, what if they are male and a junior reg versus being male and a senior reg? And what if they are female and a junior reg versus being female and a senior reg? And so when you break it into that, when you break the relationship between male and female, and this is a bad example because both of them are dichotomous. When you break that relationship into what is the impact of being a junior reg and senior reg on the relationship between being female and the number of hours worked, that is when you have interaction. Let me do something. Let me escape from here, and we're going to go back and show you what it is I'm trying to do. Okay, so you can see this. I'm going to move this a little. Oops. Real quick, Ebuwa. Hurry up. Okay, I'm going to move this, and I'm going to move, no, that one. I'm going to move this here. Good. So let's come back here. Okay, so you can see that the relationship, if you're male, so we know that if you're male and you're a junior reg, you would work maybe X number, this X here, number of weeks, of hours per week. But if you're a senior reg, and forgive me, don't look at this as look at this as not as a climb in numbers, but just a different situation. So this is your X, number of hours you work, yeah?
I look at it as nominal.
Okay, look at it as nominal. There you go, not as though it's a climb. So if you were a junior reg, this is the number of hours you will work if you were male. If you were a senior reg, your number of hours will increase, right? But if you were female, the blue, you were a junior reg, you would work this number of X hours. We've already established that males and females work differently. But when you become a senior reg, the distance between your being a senior reg and a junior reg is going to be different from the distance between the males being a junior reg and senior reg. And that is why the slopes are different. So basically, let's come back to this. Basically, you're saying that that change between junior and senior reg, and this is the summary, I like where this is going. The change between junior and senior reg in number of hours now differs if you are a male and a female. So the relationship between being your registrar status and the number of hours worked is modified by your sex or by your gender. That is what interaction means. It means that is a relationship between two variables, one X and one Y, modified by the components or disaggregated terms in a third variable. So I'm going to quickly explain what confounding is and why it is different. So in confounding, there are also three variables at the same time. But in confounding, you're saying is the relationship between X and Y modified by the presence of this variable, not by its components. So the presence between drinking coffee and bowel cancer, is it modified if this person also smokes? Does smoking change that relationship? But in interaction, you're saying that, is there a difference between the different levels? The different levels in this, is the different levels in this third variable, is the result of, I got it right the first time. It's the result. It's the result of the relationship between your X and Y variable, number of hours worked per week, and being your registrar status. Is it different from the two different categories of a third variable, males and females? A good example is the impact of aspirin on health outcomes. And the first set of studies they did, they tested it in majorly men, and they saw that it was protective. And then over time, they tested it in women as well. And I think they saw that, well, it leads to more problems, such that over time, I think the US Preventive Task Force is now saying maybe you guys should not take aspirin, because by the time you separate, when you see men and women, just men, the data is one way. But when you see that relationship in women, it's so different that they're saying maybe it should not happen. Interaction is a little tricky, even for me, but I hope that I did a good job. In interaction, you are disaggregating that third variable. You're saying, is it different for the people who have the one level of the variable versus the other level? So basically, it's as though you are stratifying, and that is how you look at interaction. You stratify your results, male and female, junior reg and senior reg, and you look at your betas, and you say, are these betas different, meaningfully different from each other? Okay, so let's jump to F statistic. I showed you the F statistic here for that regression, that multiple regression where we adjusted, and we said that it's from an ANOVA, and it says that is reported by the model output to test whether there is no significant association of the entire model. So this is the omnibus test. It's everybody, the coach, the drivers, everybody is in the bus, and we're looking at whether that works, you know. And if the test is not significant, there's no need to look at this, because your model is bad or your model is wrong. There's no need to look at this one. Okay. Selecting covariates to include in your multiple linear regressions. Be a subject matter expert. I've said that again and again. So if you're looking at intelligence and years of going to school, don't go there and throw in the shoe size of the people, unless you're a subject matter expert and you're able to say, well, shoe size could be an indication of stunting, if it is, and stunting is a predictor of intelligence. Do correlation of all your variables. So the correlation of all your variables thing is to check for collinearity. So what is collinearity? Let's see. A bad but good example is when in data sets, sometimes you calculate income earned in Naira, right? But they want to understand what this, maybe the decision maker is like, okay, I'm not sure what Naira does, you know, because this is a dollar mindset. And so the analyst will convert the money from Naira to dollar. So there will be two variables, Naira and dollar. Those two numbers will be very, very highly correlated. Maybe they'll even have a correlation of 1, but sometimes people would include income, and maybe they don't know that this is the same dollar translation of the Naira. They would include both of them in the model, and you're going to see very high correlation. So that's a bad example. It's an extreme example. But what happens when you do multi-collinearity is that it reduces your p-value for your model. So avoid including collinear or multi. So BMI and weight, that's a good example, because weight is part of BMI. So it's part of, so you're going to see high level of linear or correlation. And so either choose BMI or choose weight. Run a multivariable. I like this one. It's called backward selection. So you just pour everything into your model, and you start looking at your p-values. And the convention is that anything that is 0.2, not 0.02 or more, you can take it out of your model and leave only the things in your model that are less than 0.2. I like this slide very much. Okay. We've talked about linearity, but you see, to the point here is that this assumption does not hold. Many times the relationship is non-linear, you know. Let's see. Have we not talked about non-linearity and what to do? Yes, we have. So you see here, so this is just when we talked about quadratic. So you see that in this case, they've multiplied this by 2, and this place not multiplied. What's that thing? Squared and done the square, done the triple one. I told you I'm not good at math, but you see, basically what you're trying to capture is this relationship, or you're trying to fit this model to align with linearity. It's the same thing. It's almost the same thing. Not the same thing. I mean, just think about it as similar to when you have discrete variables, but because you're looking for the relationship, you fit it into a continuous linear regression model because you're looking at a relationship. You're not exactly saying this is the way it should be. Okay, they're called polynomials. See, I told you, I'm not good at math. So you have your quadratic and your polynomials. Okay, so the cubed one. Cube, that's it. It's called. Wait, why are we doing this again? Okay, let me look at these. Okay, let's look at this and then we can wrap it up in time. So assessing non-linearity. And so since the two-side p-value was 0.09, which is greater, you conclude, and this, which is you conclude there is no significance. So basically I think what this slide is showing, right, is you want to address your non-linearity, you run your model, but then you look at whether there is significance between the models. And this is not hard and fast, to be honest. I think that maybe what we should do is show that graph that says what should you do depending on how the relationship of your x and y when you do your post estimation diagnostics. Okay, we are 1 minute from time, and this was a intermediate level class, so it's a little difficult. It was a little difficult, but I hope that you get the gist. It's difficult to teach all this stuff in 2 hours, but I hope you get the gist, and let's have a conversation. I'm happy to stay back for 10 minutes, 15 minutes to answer any questions that you have.
Okay.
I guess we can see the recording at this point.
Okay.
Oh, that's for Ore, but go ahead, Jerry.
So I was looking at, I didn't really get the where you were talking about being careful about running to avoid including multi-collinear variables, right?
Okay.
So just to take that again, and then for the omnibus test, I didn't really get that as well.
Okay, so let's do the first one, right? So sometimes your variables are collinear or have a high level of collinearity. So I think there's a test. I think I don't remember it, but there's a test for collinearity. And I think when your value is greater than 0.9, you're going to say those 2 variables are collinear. But you can also run a correlational test for 2 variables to find out if they are highly correlated. So, and the example we gave was BMI and weight. Because weight is part of the calculation or estimation for BMI, if you get a correlation between weight and BMI, it's going to be very high. It's going to be over 0.7. If you ran that test I was talking about, again, the more I've moved away from an analyst role, the more I've forgotten these things. but you guys have those classes where they teach you the coding. So please ask them. The more you, but when if you run that test, you're going to see that your data is collinear. Weight and BMI are the same thing. Are mostly the same thing, right? Because you're trying to say, is this person obese or not with BMI? They're kind of thing. So because they are collinear, when you put two variables that are collinear into your model, what will happen is that both of them would show that they are insignificant because they are imagine that they're butting heads with each other. They're not contributing to your model. They are disgracing your model. They are messing up your model. So you're going to commit a type 2 error because there is a relationship there, but you fail to see that relationship because you've included a collinear, two collinear variables or multi-collinear variables.
So why you said why you chose weight and BMI? Of course, definitely because these two variables are definitely related because weight has a direct effect on BMI.
Yes, correct.
It's likely that there are plots. If you plot those two variables, you would see that they are moving in the same direction. Yeah?
Yes, but a lot of things could be correlated but not collinear. So that's why I'm saying when you start to see a high level, a moderate to strong correlation, which is 0.2, is a test that you want to run to check for collinearity. And I like I said, ask the people who teach the labs, they'll be able to tell you. And when you see that value that says these two are collinear, you take one out. In this case, you take weight out. You know, another thing, you eyeball your data and you see, well, we've included income in naira and income in dollars. Of course, those are the same. They're just converted. Take one out, just your income. Okay. Your other question? Yeah, go ahead.
No. I think I get.
Okay. So
we're talking about the omnibus test.
Okay. The omnibus test really is just what is the significance of your entire model. So remember that we said that someone wants to go. I mean, someone wants to contribute, not leave the chat. Someone wants to contribute, please. Okay, maybe that's an artifact. But remember what we said about when you're doing your multiple linear regression. We're saying that if we're adjusting for being female, we're adjusting for resident. We can also be adjusting for age of the resident. We can also be adjusting for number of children of the resident. So your multiple linear regression can have multiple X variables. So you have multiple X variables, and then you run it in SPSS. Before you start looking for is female significant, is age significant, look at the significance of your model. And the significance of your model is the omnibus test. If your model is not significant, then you're going to say, I don't care about all these individual values of significance. This model does not make sense. And then you can now start trying to understand, why does it not make sense? Is it because we've included collinear variables? Is it because we are not subject matter experts enough to know what variables should really be included? Is it because we just included things that have higher p-value in terms of our that have a higher p-value than 0.2? You know, so that's the way to think about your omnibus test. Why do we have a model that is not significant, and what should we do to address that?
So this is just it's actually an an ANOVA test, yeah? It's
Yes.
just an ANOVA test.
Yeah. I'm not sure
variable you want to use in your multiple regression.
Say that last part again.
Yeah, so it's just like an analysis of variance between using those variables you have used in your model.
I guess so. I don't know the technical details of what this ANOVA is actually testing, but the implication is here with the significance. You look at the significance and you say, what is going on with this model? Is this a useful model? Versus,
if you look down of the model, that you see B is stating the predictors there. Like it, the description under the table is telling you the dependent variable. No, the first table. Below it, there is a description A and B.
Right.
You are seeing dependent variable this, and then the predictors down there. It's added both the variable we use to adjust and also the female variable stuff.
Yeah. Yes, because this is your model. So this is telling you the significance of the model. So it has to take into cognizance what your dependent variable is versus what it's just highlighting to you which is Y and which are your X's.
So in this case, can we say because the description says is reported by the model output to test whether there is no statistical association in the entire model. That is so. Now the next point says that is whether all the regression coefficients in the model are equal to 0.
Yeah. Yes. So remember your HOHA, right? Your null hypothesis and your alternate hypothesis. So your statistical output is constantly judging versus your hypothesis versus your null hypothesis. And the statistical output for your model is that your model has no relationship. There's no relationship in this model. And the mathematical way to express that, what you are looking for when you run a model is the coefficients. Why? Because a model is about prediction, and your coefficients are your slopes, and your coefficients are what help you. And your coefficients are what help you predict, right? So these are your coefficients. Now, if your coefficient is 0, this is 0, this is 0. There is no relationship between your x's, including your x, including your y when your x is 0. There's no relationship between your x's and your y. So this is the mathematical translation of that statement. It helps you understand whether these are statistically 0. Statistically 0, not 0. And by statistically 0, you mean that no matter what number you see there, the significance allows you to believe that that number is due to chance alone, but that number can as well be 0.
Yeah, sorry, I'm dragging you, but
no,
the significance we see here in table 1, 0.15. It's actually less than 0.05. So it's saying that it's significant.
Exactly. So remember, this is not the conclusion. This is the question. This is stating the null hypothesis. You're saying the null hypothesis is saying that your model, the coefficients in your model is a BS model. Your model has no relationship. You are modeling nonsense. That is your null hypothesis. And that's why I'm saying that because you are modeling nonsense, your coefficients are statistically equal to 0. But you now run this, and when you get this p-value, you now say, no, we're going to reject that null hypothesis, and we're going to say our model is actually modeling a relationship. And then you come down here. Yes, you come down here, and then you say, okay, what is driving this relationship? Which of them are
so So we actually want the model to be significant. We actually want that p-value to be significant.
Exactly. Yes. Otherwise, you are going to be forced to agree with the null. And to your point,
there will be no need for a regression.
Exactly. There will be no need for a regression. And if you find that it is not significant, you now run your diagnostics and say, wait, do we know what exactly we should be including in the model, subject matter expert? Are we including relationships that are variables that are significantly correlated to one another? Do they pass the test of collinearity? And without running the test, you can just look at the variables. Again, BMI and weight. You say, oh, look at what we've done. And the last one is, did we do that backward selection? No, this is not backward selection. Backward selection is doing them one after the other. Oops, I said it in the class, backward selection. But you say, did we run these and throw everything into the model?
I was about to come to that.
Yeah, okay.
What was the difference? There's a lag between our network, so pardon me.
It's okay.
It seems like I'm interrupting.
Okay.
This run multivariate linear regression, how and remove all variables with a p-value of greater than or equal to 0.2. How is that different from the actual multiple regression that we are doing?
Good. It's a good question. And let me see. After the wrap-up, is there anything? I think that we included some slides that were not supposed to be. That's what threw me off, because we already addressed this. But there's something called parsimony. Basically, you're saying, do we need to have our model more efficient versus do we need a big model? So let's see. Let's come here. Let's come back here. So imagine that we added age of residence, age at birth. Age at birth is always a wrap, so I'm joking. Age at joining the hospital. Whether they're married to a man or woman. You just add all this stuff, all the data you collected. Why? Because maybe you don't have a lot of expertise in this area. So you throw in all the data, right? If you throw in all the data, you start to ask yourself, is this really efficient? Or are there some variables we can leave out? And that's, you are looking for parsimony. You're looking for your most efficient, Another thing this helps you to do after you have looked for multicollinearity is it helps you achieve parsimony. But it's a good question. What's the difference? Is that not your multiple? Yes. But you don't just want to run a multiple linear regression. You want to run a parsimonious multiple linear regression.
And then you can take out variables that's okay.
Yes, that are not parsimonious. Yes.
Seems like there's a few more slides that we didn't.
No, there's a lot. So all this stuff that we've just done. When I was doing my intermediate stats, this was maybe 3 or 4 classes, and each class was 3 hours. So this is a lot of my jumping some things, not explaining in depth. No, this is clearly not everything that you need to know about this.
I saw a slide on evaluating models. Okay, yeah, just go and do some other reading.
Yes, please. Yes, please. Yes, go do some other. Let me see. Evaluating. Did I skip that? Evaluating models. No, this one. This is where we talked about this. That's your homoscedasticity and your residuals versus let me see what does it actually say? Normal QQ. So this is of course your
So this is the QQ. So I was even saying this residual. When you predict the model, you are supposed to have those residuals come out as numbers, right? On maybe like a variable too. But
yes.
How do you run all of this? Is it the software you will ask to create
Yes.
a variable residuals, then you now run again the QQ
Yes.
using that residual.
Correct. Correct. Very correct. After you run, in fact, I think that maybe the instructors for this course, we have to do a refresher. But I don't think I want to. But after you run your model, there is a simple code you just type, right? Predict, it's called predict in Stata. You just type predict, and what predict will do is it will give you your y hat and the residuals, right?
Okay.
It will, yes, and then you can now say scatter. I'm using Stata code. They're just going to say scatter predict and rs. I think that is called, you say predict rs comma rs, predict y hat comma y hat or something. I've forgotten those codes, but they are predict, and then you say scatter y hat rs or res, and it will give you these things. Or you can say qq, this and this, and it will give you those things. So yes, you are correct. You have to generate those variables after you have run your regression. So fine.
Okay, thank you very much.
Okay.
Thanks for the extra time.
Yes. Anybody else have a question, or are we ready to go? Okay.
No, our question and answer session was actually recorded. So.
Oh, okay, good. All right. Thank you, everyone. This has been really good. And Aura, please let me know if I'm teaching another class so I don't find out very late. It was my wristwatch that said, "Hey, you have a class tomorrow." I said, "Oh my God, do I?" I'm not going to tell you where I was when my